Hi everyone, I'm excited to be here to talk about heap exploitation. So I'll be discussing Scudo, that is Android's hardened memory allocator. What is Scudo? Scudo is a user space memory allocator. Basically, it implements the dynamic memory allocation and deallocation APIs, so malloc, free, etc. And what's interesting about Scudo is a hardened memory allocator. At least that's what it says on the Android developer website. What is a hardened memory allocator? Basically, the allocator is designed in a way to make the exploitation of heap-based memory corruption vulnerabilities very difficult, prohibitively expensive, ideally. Why is Scudo relevant? Scudo is relevant because since Android 11, if you download the Android open source project and you compile it, Scudo will be compiled into your standard library, and then all of the user space program will use Scudo as their memory allocator. Before we started this project, we had another project that was going on, and we had a bunch of crashes in Android apps, memory corruption vulnerabilities on the heap, and these apps are running on devices that were using Scudo. But at the time, we didn't really know, but at the time, we wanted to know, okay, are these vulnerabilities actually, exploitable? But in order to do that, we needed at least two things. We need to understand how does Scudo actually work on a very low level. So how does Scudo actually manage the heap? What do Scudo memory chunks look like, etc. And then, because we had a bunch of these crashes, we wanted to know, okay, is there like a general exploitation technique that's that we can leverage across all of those apps? And basically, these general exploitation techniques will be targeted against the allocator because that's like the common thing between all of those apps. If we could leverage these memory corruption vulnerabilities to basically exploit the allocator and get ourselves an arbitrary write or code execution that way. 1 and 2 are synergetic, so basically we started this project looking deeper into Scudo and trying to see, okay, can we actually exploit the allocator? Now for the rest of this is the outline for the rest of the talk. I'll quickly explain a bit more what I mean by exploiting the allocator. I'll go into Scudo security measures and internals. I'll talk about Scudo in the context of Android, and then I'll actually talk about exploiting Scudo. Okay, so first off, here's the 3 components that are kind of involved when it comes to exploiting the allocator. You have the application, that's code written by the developer. That application uses malloc, free, etc. to basically get some dynamic memory. Whenever it calls these APIs, control is handed to the allocator, and the allocator then manages the heap memory. All these 3 boxes are part of the same user space program. It all starts with the developer-written code being buggy. So there's bugs in there, and these bugs can be used to trigger memory corruptions on the heap. So overflows, used after freeze, etc. Whenever these memory corruptions are triggered, you might be able to corrupt inline heap metadata. What's inline heap metadata? Basically, this is data that's not application specific. Instead, that is data that is stored there by the allocator to basically keep track of the heap state. So you corrupt this inline heap metadata, and then when the allocator interacts with that corrupted metadata, there's like more or less 3 things that can happen. First thing is the allocator just crashes. Second thing is the allocator stops because it detects something's wrong. Or the third thing is it basically gets turned into a weird machine. And the third option is the one we're interested in because that one can be exploited to basically make the allocator do things like allocate a chunk at a chosen address, for example. And for the standard Linux libc allocator, there's a lot of different, there's a huge library of techniques on how to do this, how to exploit the allocator. But there's no such thing for Scudo. And basically, we try to answer this question, okay, we can corrupt some memory on the heap. And if Scudo interacts with that memory, can we actually turn Scudo into a weird machine? Because the thing about Scudo is that Scudo is supposedly specifically hardened against such attacks. So I said before that in order to actually exploit the allocator, we need to understand the internals. I'll talk about internals here. We have 2 security measures, randomization and protection. And then we have basically the 2 types of chunks that Scudo handles, are normal and large chunks. So first off is randomization. This is a security measure that basically prevents heap feng shui, or basically the Scudo randomizes the layout of chunks on the heap for every time the program is run. And this basically prevents attackers from predicting the heap layout. The second security measure is protection. Protection is basically, so I talked before about inline heap metadata, which is very interesting for attackers to corrupt that. Scudo tries to prevent that by basically signing inline heap metadata. And then every time Scudo interacts with inline heap metadata, it verifies the signature. And if the signature fails, Scudo directly aborts the process and will not further process this metadata. Scudo handles two types of chunks. Normal chunks are chunks that are actually allocated in the heap memory region. These are chunks less than 65,000 bytes. And for these chunks, Scudo stores just one piece of inline heap metadata, the chunk header. These are 8 bytes just before the chunk body. The chunk body is where basically the program stores the data. And this chunk header has 3 fields, the size of the chunk, the type of the chunk, whether it's a normal chunk or a large chunk, and the state of the chunk, whether it's allocated or freed, and then also the signature protecting that chunk header. There's another type of chunk. These are large chunks, bigger than 65,000 bytes. These chunks are actually not allocated in the heap region. They're instead mapped in their separate memory region. And this is the structure of these large chunks. There's the chunk body. On both sides, they're surrounded by guard pages. These are just the memory region with no permissions. And then there's also the chunk header. This is the same as for normal chunks, but then there's also the large chunk header behind the chunk header, and this large chunk header stores some additional metadata Scudo uses to track these large chunks, which is the size and address of the large chunk, and also pointers to a linked list of other large chunks. This large chunk header is very interesting because it's not signature protected, and it stores pointers. The problem is that it's in a very inaccessible location. It's not on the heap, it's in a separate memory region, and it's kind of surrounded by guard pages, and it's also behind the chunk body. So you need a fairly powerful memory corruption primitive to actually touch this, and we just assume we can corrupt heap memory, so we cannot actually directly corrupt this large chunk header. All that said, looking at these security measures, exploiting the allocator looks kind of difficult. So there's the only corruptible inline heap metadata is the chunk header, and that one only stores like very few fields and is protected by a signature. So what do we actually do here? Let's take a step back and actually look at the significant deployment of Scudo, which is the Android user space. So here we have a bunch of processes running in the Android user space. What's interesting about the Android user space is that actually a lot of the processes running there are clones of the same process. They're cloned from the so-called zygote process using the fork system call. Why is this the case? So all the processes so all apps are forked from zygote, as well as some more privileged system services. Why is this the case? This is a performance optimization because, for example, apps rely on a huge amount of framework code and data. So it's about 4 gigabytes of framework that's being loaded. And if you have a lot of these applications running at the same time on lower-end hardware, you might start to be worried about the memory pressure on the system. The thing is, if you clone a process using fork, basically the underlying memory pages that are not touched are shared. So read or read-execute pages are shared. And so if this way, you basically reduce the memory pressure if you have by forking them from the same process and having a lot of the memory actually shared across these. Furthermore, fork is very fast, so you start an app even on a low-end phone. Actually, the app starts more or less instantly. So great performance hack. What's the cost? The cost is security. When you basically clone the process using fork, it's the exact same copy of the process, and basically looks at the return code of fork to figure out, am I now in the parent or the child process? And then it'll either keep executing zygote code or the app-specific code. And the thing about when you do this exact copy is you have the same ASLR layout. So you have the same ASLR layout shared across all of these zygote fork processes. This has been known, but is obviously a big problem. The thing is also you copy the memory contents. And the memory contents contain the secrets that Scudo actually uses for its security measures. So it contains the seed that is used to randomize the heap layout and the key that's used to sign inline heap metadata, and that is basically propagated to all zygote forked child processes. And well, this is a huge issue because obviously now when we look at a sort of attack scenario where we're attacking from one zygote fork process to another, basically these two security measures I was presenting before become invalidated. We have shared ASLR and the shared randomized secret, so the seed that is used to randomize the heap layout. So given a sequence of allocations and deallocations, you basically, like the evil app attacking a victim application basically knows the exact addresses of where chunks will be allocated. Furthermore, because the secret is shared between the victim, the secret used to sign the inline heap metadata is shared between the victim app and the target app. The attack, like if there's a way to corrupt, basically the attacker app has a way to forge valid signatures. And this sort of zygote fork to zygote fork process attack scenario is relevant because it includes malicious apps, and because apps are kind of like you download them from somewhere, they include a lot of dependencies. So it's this like a valid threat model for Android, and in this valid threat model, and you know, attacking other apps could be a way to escalate privileges. Also, there's some system services that are zygote forked that have like more privileges than apps, and so attacking these is also a valid target for privilege escalation. And so to conclude this part of the talk, basically, in the most significant deployment of Android in a sort of very important attack scenario, Scudo's protection are basically more or less useless. Now, we're not quite done yet. We need to do some legwork to actually exploit Scudo. And here I basically give you an example of how you would exploit Scudo in this attack scenario, given a heap buffer overflow. So first off, the attacker app interacts with the victim app and arranges the heap layout in a way such that the chunk where the overflow occurs is before the chunk that the attacker wants to overflow into. And this is possible, of course, because, again, ASLR and the randomized secret is shared. So you can predict the addresses where chunks will be allocated, and you can basically trigger allocations, interact with the target program a bunch to get this desired heap layout. Then the overflow is triggered, and the victim chunk header is overwritten with a new header. This header is signed correctly because it's signed with the same key that will be used to verify the signature. The only thing the only field that is changed in the header is the type of the chunk will be changed from a normal chunk to a large chunk. Now, when Scudo interacts with the victim chunk and tries to free that victim chunk, Scudo will first verify the signature of the modified header. This is going to succeed because, again, it's been signed with the same key secret that is going to be used, that is used by the victim app to verify the signature. It'll then start parsing the contents of the header, and it'll see that, and Scudo will see that this is a large chunk. And then it'll go sort of behind the modified header and look for the large chunk header. And this is obviously a disaster because here it's just the large chunk header is replaced by just attacker-controlled data. And well, in this case, Scudo would crash because it would dereference a pointer at a bunch of A's. But if you're smart, you forge a large chunk header that is in the right way, you can basically turn Scudo, you can basically get Scudo to allocate a chunk at your chosen address. So in our paper, we have two techniques where we basically tamper with different fields in the chunk header. The forged commit base modifies basically the address field of the large chunk header. This address field is directly put into a free list. So you can basically get a chunk, put a chunk at your chosen address into the free list. The only requirement for that is you need to then be able to allocate a large chunk. The second technique modifies the pointer to the linked list of large chunks. Basically, for this one, it's a bit more complicated. You need to forge a fake linked list, and then when this the victim chunk is freed, there's an unlinking takes place. You write a pointer to where you forged your fake linked list. You kind of set up the heap in a way so you have this is inside of a free list of another free list, and then you have a chunk overlapping that other free list, and you get control of the free list, and you get arbitrary right this way. If you're interested in details, please refer to the paper because I don't really have time to go into all of the details here. So you might be wondering, okay, I talk about all this stuff. Is this actually like a realistic problem? Is this actually feasible? Is this actually possible? So what we did is we basically backport an old CVE. This is like a heap buffer overflow/underflow to Android 14. And then we exploit that heap buffer overflow in the system server. The system server is also a zygote fork process. it runs a bunch of system services that basically expose APIs to apps that basically apps use to interact with hardware of the phone. And we basically have a malicious app that does an IPC with the system server, and in 2 IPC requests leverages one of our techniques to basically get Scudo to allocate a chunk on the stack. And then we write a rock chain to the stack. When the system server returns, we hijack the PC, we execute our own code using return-oriented programming. Yeah, so this brings me to the end of my talk. I discuss Scudo in the context of the security of Scudo in the context of Android. We show off some exploitation techniques against Scudo. We have a case study targeting the system server on Android 14 to show that this is realistic. If you're interested in this, we have a repository with a bunch of tooling to analyze Scudo, so a GDB plugin to look at the heap state, some heap menu programs to play around with the exploitation techniques, and also the source code for the case study. Thank you for your attention.
Thank you very much.